I've ended the fun here. It's my pleasure to introduce Charlie. If anyone on the line doesn't know Charlie already, then that's unfortunate for you, and you should seek to rectify that situation as soon as you can. Charlie's a great guy. So Charlie got his PhD at the University of Bern, if I'm recalling correctly. He is a co-I on stereoplastic and the lead co-I at UNH on wind. Charlie teaches the magnetospheres course, and also at least used to teach half the plasma physics course, which is great. I will always remember Vlasov as the Mick Jagger of plasma physics because of Charlie's course. And I've been working with Charlie recently through his work that he's doing on the MMS mission, which a recent result of his on MMS is what he's here to tell us all about today. So Charlie, with that, I will pass it off to you, and you can get started whenever you're ready.
Oh, thanks, Kevin. So I hope you can hear me well.
Just fine,
yeah. So the subject of my talk today is to discuss an encounter by MMS at a flapping and twisted tail current sheet of the ion and electron diffusion region. I would like, first of all, to give special thanks to Anthony Rogers, Roy Torbert, Kevin, and Takuma, who were main co-authors in the paper on which this talk is based. So the outline is, so we will talk how MMS observes a twisted and flapping tail current sheet on June 17. We would like to know what does that mean? How do we know? Then we do a magnetic field line curvature analysis to study the geometry of the current sheet. Then we prove and give evidence to show that MMS actually encounters not just a reconnecting current sheet, but actually it enters this diffusion region, which is found embedded in the ion diffusion region. We show that the MMS path is crossing the EDR in an approximately perpendicular direction earthward of the X-line. So we don't have the usual situation of the X-line going over the spacecraft back and forth. And then we show the results of two-dimensional Dpx simulations done with initial conditions to tailor to this event, and we compare with the MMS observations. We get the reconnection rate, which we infer from the observations and compare with the simulations. And therefore, the morals drawn will be that steady reconnection and 2D are good representations of reality at the locale sampled by MMS. And to give the larger context, we look at a likely cause of the flapping motions and what is the associated geomagnetic activity. So first of all, a quick word on Oncologist Reconnection. So this is a diagram from Pashman 208. So of course, in the magnetosphere, we have typically 3, but they show 2 here. Reconnection here at the day side, and reconnection in the tail. We are speaking particularly of the tail today. And this is the 2D view of symmetric reconnection. So we have ions decoupling from the magnetic field in the ion diffusion region. And later, the electrons here decouple from beyond a smaller electron diffusion region. And this decoupling gives rise to whole fields. In the magnetic field, you have quadrupolar out of plane fields. And in the electric field, in the red arrows here, you have in the normal component, you have a bipolar EZ, which is pointing towards the current sheet center from both sides. So when we want to show that we are crossing the IDR, we will look for this whole structure and also the breaking of the frozen condition. Of course, asymmetries and guide field can alter this whole pattern. And this is a long, long story. For example, they can become stronger on the low beta side. Now, the thing is, although we are in the tail, we do have some asymmetry and a small guide field. And interestingly enough, we shall be able to see these alterations of the whole pattern very clearly too. And now just to concentrate on the electron flow behavior, which we will need. This is the red and blue arrows here. The blue arrows are the low energy electrons, which travel along the separatrices towards the X line. And the red arrows are now the high energy electrons, which are moving opposite to this, and they have been produced and energized near the X line. This was the first evidence, the first observational evidence of diffusion region in the tail was given by Nagai et al. in 20 years ago. And then we come to the flapping sheet by MMS. What did they see? Oops. This is an overview plot of a 40-minute interval. What is flapping, first of all? Flapping is nothing but an up and down motion of the geomagnetic tail. This was noted soon after the tail, the geomagnetic tail was actually discovered. Soon after, in 67, people noticed that the geomagnetic tail has a tendency of flapping up and down, of going up and down. How do they know? Well, if you have a spacecraft close to the tail, you would have polarity changes in the Sun-Earth component of the magnetic field as you go above and below the tail. Like you have here, here for instance, this 40-minute interval, you have the spacecraft is here north of the tail, south of the tail, north, south, north. You have 4 clear flapping instances. And each one of these lasts for a few tens of seconds or a few minutes. And this is all very fine and dandy. You say this we know already. However, you see, there is an exception to this here, which is happening at this arrow here. You will see here, this is much sharper. And indeed, you find that the crossing from south to north here, it took only 1.5 seconds, which means we have a very thin current sheet, which means also that we don't just have a flapping. There is something more to it than just the flapping, why it's so thin. And that is what we want to discuss here, that crossing over there. So first of all, the configuration of MMS, where is it? It's in the near tail, about X minus 20, and on the dawn side, so Y is negative. And so this is a, here on the right, we have a picture of a BZ transition in the field and how it is seen by, when it is seen by the various spacecraft. It is seen first by 3, then 4 and 2 almost together, and then MMS 1. So if we look at the positions here, 3 is up here, green, 2 and 4 and 1. So the disturbance caused by the flapping is traveling towards dawn. It is traveling towards dawn. And this is exactly the second condition implying flapping. When flapping is up and down motion associated with a perturbation which travels downwards. Indeed, looking at the figure here on the right, we can see that this perturbation covers 25 kilometers in about half a second. So we have that the flank-wise speed, the speed towards the flank, is about 50 kilometers per second. Then we look at the magnetic field curvature, which is this quantity here, where B is a unit vector along the magnetic field. The panels, the top panel is here for reference. The second panel is the curvature of the fields. And you notice that in these yellow dashes here is where you cross the current sheet. There are four instances here. And you notice the curvature becomes very, 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 very big, this curvature here. Highly curved, large at each side. However, this one, the one which we care about, is the second one. It is the biggest of them all. Then we have the radius of curvature, and correspondingly, the radius of curvature gets smaller and smaller and smaller. And here it is the thinnest of them all, and it's having the smallest of the crossings. And the last one shows the tilt of the current sheet here. And in our crossing, the tilt is about 80 degrees. So you have a very tilted current sheet towards dusk. And if we take a closer view here, so we have the temporal profile of the curvature parameter kappa, which is the ratio of the radius of curvature of the magnetic field over the gyro radius of the electrons. And you will find here that our event is at 2407. Here, the maximum gyro radii are larger than the minimum radius of curvature at around this time, which means that around this time, we have a very thin current sheet where the electrons are no longer coupled to B because their gyro radii is larger than the radius of curvature of the magnetic field. And now, of course, we need to use a coordinate system which is more useful for us. So we go to a coordinate system centered on the CS. We do a minimum variance analysis on the magnetic field data, high resolution, on this interval here, and we get these results. What strikes us is that the normal component is mostly in the GSM-Y direction. See, it's pointing towards dusk. This is the tilting which we just saw a moment ago. Now, these LMN in this context are referring to L is the direction of the reconnecting fields, M is the direction of the reconnecting current sheets out of the plane, and N is the normal. Now, you will tell me, okay, so you determine this element. How do we know that this determination is robust, is good? Well, typically for that, you look at the intermediate to minimum eigenvalue ratio. We have a value of 16, which is taken to be large enough for this result to be robust. Okay, so we have this conclusion here. So we can use this element coordinate system. We can do some relevant scales which we will need in the analysis. First of all, is the current speed, the current sheet speed along its normal is 63 kilometers per second. This is inferred from the crossings of M1 and M3. It's a simple algebra, which is need not belabor the point. The normal width of the EDR, also by a simple calculation, is found to be 44 kilometers, which is about 9 electron inertial lengths. And if we take the minimum radius of curvature as an estimate of the half width of the CS, we have that at near the X line, the width of the CS is less than 44 kilometers near the X line. No wonder that the crossing was so short, in other words. Now here we have the electron, we talk about the electron behavior here. So I have this 8-second period and this figure here with the components of B for guidance, okay? The total B, and this dashed line here is the guide field. It shows you when you are in the inflow region here, you still have a non-zero component. Then this is density and temperature, etc. And in anticipation of results, these vertical lines here between the outer ones, that is the IDR, and between the inner ones, that is the EDR. First of all, we notice here, if you look at this one here, you see small asymmetries in N, T, and B. For instance, here, it is denser, the plasma in this inflow region is denser, hotter, and in a weaker magnetic field. You tell me, well, that asymmetry is not very big. It is not very big, of course. However, we will find its effect. Here we have a case, this last but one panel. This shows an electron jet peaking at so-and-so. Mach number is 5.5, out of plane direction M. That is good for an EDR identification. And here we have a flow reversal in the E flow here, but this is not reconnection related, you see, because if it were reconnection related, you should have an associated BN reversal, which we do not see. So this is likely due to an ambipolar electric field, which we see here in blue. You see the ambipolar field, which okay. So if we have no flow reversals, we can conclude that we are not going from one side of the X line to the other. So fair enough to ask the question. So on which side is MMS crossing the current sheet? And here we have this picture here. Remember, we showed a picture of what the electrons should be doing. And here we have that before, these are the MMS 3, 2, 1, okay, in this order, as we saw first, like that. And here we have the low energy electrons. And you see that initially they are flowing along the field, parallel to the field, and after they are flowing anti-parallel to the field. So if we make a rough drawing here, they would be something like this. Initially, they are flowing parallel to the field, and afterwards they are flowing anti-parallel to the field, which means that the crossing MMS did is on the earthward side of the X line. And now we look at this figure here. Oops. We want to show identification of the IDR, ion diffusion region, first in this picture here. And we have, first of all, we plot this ion adiabatic expansion parameter, the current density in the M direction, the normal electric field Hall, and the electric field, the magnetic field in the out of plane direction. And we can see, first of all, in this adiabatic expansion parameter, which is the perpendicular electric to magnetic forces, when this is bigger than 1, this is a good indication of ions being not frozen in. So it gives us a rough idea of where the IDR, the extent of the IDR. This rough idea is confirmed by the JM, which is maintaining the Hall fields, which is also in this part. And then you have the Hall fields. You have the EN here, pointing on both sides to the current sheet, plus and minus. Then you have the Hall field, B field, which is BM minus the guide field here, which is negative to positive. Notice that in the Hall fields, before the current sheet crossing, the EN and the BM are smaller than after the current sheet crossing. And this, as I told you before, this is a sign that we are feeling the small asymmetry in N and B. That's why these are not the same. Question is, will the simulation reproduce that? That is a question. And then to show further the decoupling of ions and also electrons, so one proof of IDR and EDR, we plot here the velocity of the protons in red and of the electrons in blue, the components thereof, element, which are perpendicular to B, and the convection flow. When they depart from the convection flow, you have demagnetized protons or ions. So in this wider region here between the orange lines, you have that P perp departs from the black trace here, and in between the green lines, it is the blue trace which departs from the black trace, which means this is the IDR, where the electrons are still coupled to the field, and this is the EDR, where even the electrons are decoupled from the field. Now we give identification of the IDR. We do it in two figures. Here I have many parameters plotted. This is just for the top panel is just for reference. This is the protons, behavior of the velocity and temperature, and you will notice we have no ion jetting in the L direction. And this is consistent with the spacecraft trajectory, which is crossing the EDR close to the X line. Because if you are very close to the X line, ion acceleration cannot yet be seen. You have to go further out in the outflow region to see that. And then at the MMS location, though, there is no evidence of heating of the protons either, this part here. Then there is in this panel here, the temperature panel, you will see there is a temperature anisotropy. with the pearl, the red one, being bigger than the perpendicular temperature. However, this anisotropy, interestingly enough, it vanishes, it disappears in the EDR. It is indeed one signature of the EDR, because the electrons are no longer tied to the field and they are scattering in that region. And then we have also this prominent field-aligned flow, which we discussed earlier. Looks like a reversal, but it's a field-aligned flow. And you have the E parallel with the error bars, which you have here, showing that in this region, the E parallel is real. This is a level 3. And this is the reconnection electric field, which we will return to in a moment. And this is the second figure showing the identification of the EDR. This is for reference, the top two figures. Then you have here in the center of the EDR, the current is primarily in the anti-parallel direction, as you can see. However, in the IDR outside, you have a shoulder-like, you see, it is more in the perpendicular direction. Most important of all is this J.E term, which is the energy transfer term in the electron rest frame. So it is E dash is given by this thing here. Now, in the EDR, you find there is a positive, this thing is positive, which means that there are energy going from the electromagnetic fields to the particles. This is one signature of the EDR, by the way. At its edges, however, you will see here at the edges, this quantity becomes negative, which means you have generator regions here with J.E dash is less than 0. Tom Payne will talk to you about this in some other seminar, I'm sure. And interestingly enough, the largest energy transfer is not in the EDR actually happening, but it's actually happening here, happening outside the EDR, where we see these so-called reversal of the flows happening. So now we turn to the reconnection rate. This is the reconnection rate. Here I follow a procedure of Kevin procedure, which he explained in his paper about the accuracy of the determination of the reconnection rate, where he used several coordinate systems and made a very, very thorough analysis. So first of all, what is the reconnection electric field? This is the EM out of plane component in the velocity frame co-moving with the X line. So it is EM plus the velocity of the X line cross B, the M component thereof. That is fine and dandy, of course, but there are possible errors. We just mentioned two possible errors. One is the error in the orientation of the X line. This is a serious problem, because this element coordinate system, which we so need to be able to understand the whole fields, for example, can have a small error in the X line. We say, well, a small error, theta of the small rotation error, orientation, will result in large errors in the reconnection rate, unfortunately, because EN, which will contribute to these, is a major contributor and is typically much larger than EM. And the second source of error is the velocity of the X line. For us, the largest error, because we have a normal crossing, remember, is BL times VN. So back to this rotation business, because this requires some care. We rotate the LMN by an angle theta, go through the motions, take the simplifications, etc. We get this, and now we find a linear fit of this quantity against EN. And here is the linear fit being done. Let's take the middle panel. The middle panel corresponds to one for the normal velocity, which we actually saw in the data. So when you do this, first of all, you see that and we use all spacecraft, we use all 4 spacecraft data, and we take the EN in the range -5 to 5, because EN is a troublesome fellow, being large. And you have the result, this result here, how much the reconnection electric field is. Now, besides the normal velocity which we determined, we also take an error to this one, error of 20. So I have here is 40 minus 63, and this one is 80 kilometers per second. And we take the average of all this. First of all, and we get this result. And I would like to say that the correction to the slope is in our case insignificant, really, very small, because as you can see from the fitting lines here, the slopes are very, very small, corresponding to a 1 degree orientation error. So that is fine. So we have the ER. And then people, of course, do the dimensionless reconnection rate so they can compare. We take for this one, we have to divide what we have found by the alphane speed and the magnetic field strength in the inflow region. But we have to make sure the inflow region is steady, of course. And we do have a steady interval here. That's very good, because you won't always find a steady interval. And we multiply by these two quantities, we divide the ER by them, and we get the dimensionless reconnection rate as this. Now, the question is, this is very fine and dandy to write a number and an error. But the point is, does this agree or does it not agree with the simulations? That is the question. And we have to be careful and perhaps a little bit patient. So here we have the 2.5 Dpx simulations. Okay, I will just go quickly through this part. Yeah, fully kinetic particle in cell, of course, performed in the XZ plane, which for us is like the LN plane, of course. And they started from a simple Harris type current sheet. Initial parameters are made by referring to the observed quantities. A mass ratio is this, boundary conditions periodic in X and conductive walls in Z. And we started off with a weak magnetic field perturbation. And let's take the overview of the results. If you look at these three panels here, on top, we have a typical Hall signatures in the BY component, quadrupolar. In the second one, we have dipolar components of EN. So that it is fine. And in the third one, we have a strong out of plane velocity flow of the electrons. That is always fine. Now, this is the probe here, the probe path. How did we obtain the probe path? The probe path is used by, first of all, we find its distance from the X line, if you will, by matching the out of plane velocity in the simulations, to the observed out of plane. And then we set the angle with the Z-axis as large as the observations. And if we recall, I'm not sure I mentioned this one, but the spacecraft MMS 3 and 1 were crossing at an angle of 18 degrees to the normal. This is where the 18 degrees comes from. And we find that the path crosses the region earthward of the EDR. And let's see what it sees. What it sees here, so here we have the components of B, the components of V, the EZ, and the temperature. In between the negative to positive BX variation, sorry, we have first of all this one, a moderate, this red one, and the strong, this green one, also with this funny profile, out of plane flows of the electrons. Here you have the dipolar electric field normal to the current sheet, and you will notice that it is stronger here than it is here, and longer too. And here you have the anisotropy, which we also saw. There is an anisotropy on these sides, but it disappears at the EDR. So we can say that these variation patterns are very similar to the observations. Let us see how similar they are. On this one, you have the simulation, which we just have been looking at. And on this side are the observations of the same quantities. And the I, as we say in Malta, or as they say everywhere, I guess, that the I is the best measure of things. Look at the I. I sometimes have difficulty telling you it's like I'm seeing two identical twins. Notice, by the way, that the simulations also reproduce the asymmetry in the E, etc. Okay, so what is the moral we draw from this? These consistencies indicate that the 2.5D geometry on which the simulations are based is a good representation of reality, at least the reality being seen by MMS in the locale where MMS is observing reality. Which is a good conclusion. And what about the reconnection rate? I hear your strangled cry. Well, this is the reconnection rate from the simulations. You see, there is an onset here at 10 inverse ion cyclotron frequency. Then there is a rapid rise, then a small undulation here, and then it kind of settles, saturates to a value of 0.085 here. So this is the evolution of the dimensionless reconnection in the simulations. The thing is, of course, the moral of the story is the following. The dimensionless reconnection rate is in very good agreement with the observations. Here we have 0.085, and there we had 0.077. This is rather good. Cause for celebration. Number two, the simulation time at which the simulation results are compared with data is in a nearly steady state. Notice steady state. The reconnection rate is not increasing much. Steady state of reconnection with a nearly constant reconnection rate. And the third one is, in addition, the consistencies indicate not only that the reconnection signature seen in 2.5, the simulation really occurred in this event, but also that the observed reconnection process was in a nearly steady state. This I repeated number two, because it is such an important point. Now, so that is the kinetics of this event. Now we come to broader pictures. Yeah, one of them is over there. People have always tried to associate or to see if it is flapping with geomagnetic activity. So here we have a look, in particular substorm activity. Here, the takeaway message at the bottom here, the flapping, in our flapping, it is associated with a substorm onset. It is also the only substorm in summer. Let us see how this goes. First of all, we have the image chain magnetometers. They are situated, the Norwegian channels here. At this time, they would be at 23 magnetic local time. This is a bonus from heaven, truly, because 23 MLT is the place where Akasufu in 1964 noticed that this is the ideal place to see a substorm onset. And even more so because Tony Rogers, only a year or so ago, showed that 23 UT is where you are likely in the tail to observe reconnecting signatures, reconnecting current sheets, IDRs. And what do you see here? You see a clear in this range, 67 to 68 degrees, you see a clear activation of the westward electrojet. You see this one? You tell me, what is this westward electrojet you are mumbling about, Farrugia? I have a picture here. You have a dawn to dusk cross tail current is deviated at substorm onset, is deviated through field aligned currents here and goes to the ionosphere. This is the electrojet here. This is this diversion is called the substorm current wedge, and here is the westward electrojet in the ionosphere. That's giving rise to these signatures here in the ground. And at the same time, we look at the indices here, the auroral AL, AE, and the polar cap north index, and we see clearly that there is a substorm onset here. A substorm onset at this time, and at the same time, the PCN index shows you the strength of magnetospheric convection. And it tells you here that magnetospheric convection has become stronger at this time, has picked up. These are all good news because, for instance, on the PCN index, Cowley and Lockwood some years ago, in the 1990s, they wrote a paper showing that magnetospheric convection is driven by two sources. One is on the night side and one is on the day side. In our case, it is clear, we agree with them now, and we say, yes, in our case, we have an intensification of magnetospheric convection due to reconnection on the night side, which you have just seen. Then a nice question, a side issue, but when you think about the many, many years people spent, and they were not even to the present day, they are not sure, asking what causes the tail to flap. There were over time, the ideas varied on this, many possible sources, many possible sources. First, people were talking of external origin, solar wind. Then they went into internal to tail origin instabilities for many years, but then this external origin returned a la mode, sort of, yeah? So you have and one of these external origin are deflections in the Z component of the solar wind flow. Why? Because this gives rise to a north-south pressure imbalance within the tail, which can cause the tail to flap. So it is fair enough for us to, instead of, to look to say, do we see something in the VZ component of the solar wind flow to which we can attribute the flapping? So here is the wind spacecraft. 1 hour data here of the wind spacecraft. And you will see here on the top 3 panels have in black, the magnetic field components. In blue, we have the flow components. And notice VZ here. They are very nicely correlated, by the way, the B and but the VZ is here. We have a non-zero VZ. And it's varying, kind of reminds us of the very first picture, right? Where we had four cases of flapping. And then we have other components like the total B, the velocity, which are interestingly enough, very, very steady, very steady. So if anything is being caused by this solar wind, it will be these components here, stable plasma components. When we now want to know the delay it takes for this to arrive at the magnetopause, we do an MVA analysis and we find that these here are actually in a plane, which is oriented towards dawn at 77 degrees. So then you will find that this structure will hit the dawn side magnetopause in an estimated 37 minutes. When you add 37 minutes to here, you will find that this will arrive, its front will arrive a few minutes before the episode of tail flapping is observed by MMS. We say this is rather neat, isn't it? So what conclusion do we draw from here? This solar wind disturbance in the north-south flow component is in our case a very plausible cause of the tail flapping. Now, earlier on, we saw the reaction of the protons, right? That the proton velocity was not picking up, and we say that's because it was very close to the X line. But we also saw there was no temperature increase. Now, there is a very, very interesting picture of the tail taken by twins in the near tail region, which shows heating of the ions 10 minutes around the time that MMS encountered the EDR. However, while the heating is very clear, it is not at the same location as MMS. That's a bit bad, of course. But when you think that the line of sight mapping to generate these plots was using a quiet Fairfield model, you will say, well, what do you expect? Do you expect the mapping to be correct? So we can say there was ion heating around our EDR encounter, but the location is likely not accurate. So what can we draw from this one? Given that, one, there is a lot of tail flapping, and two, there was no other activity observed. And for this, I refer you to the Omni database. For 6 hours, the only recorded activity was the one substorm we have just seen. Otherwise, there was nothing. So the observation of twins is likely to be related to the same event seen by MMS, and the disagreement in location is due to a projection mapping issue. So this is there are some qualifications to this, obviously, but it is to my mind, it's a strong point given what the level of activity was. And now we return to the effects of asymmetries in the whole field. Remember that in the tail, typically, you don't expect asymmetries in the tail, but we did have some small ones as we say, in B and E and TE, to which the electrons were denser, hotter, and in a somewhat weaker magnetic field before decrossing. They were in a lower beta after decrossing. This is important because if we go into the theory behind what's happening here, the lower beta tells you what is the side where the stronger effects are seen. And in our case, we find that on the low beta side, after the CS crossing, the EN and BM are clearly stronger. And this was also present in the Dpx simulations. So as a subsidiary point, I suppose. So now we come to the conclusions. We analyzed MMS data during a rapid traversal of a flapping and reconnecting current sheet in the near tail. The guide field was small. I have not mentioned this much, but the guide field was small. The current sheet was highly tilted. Its normal was towards dusk. And its extreme thinness, which was something like 40 kilometers, recall, was confirmed by a curvature analysis of the magnetic field lines. Using the pitch angle distributions of low energy electrons, we show that there is a crossing earthward of the X line. This is rather nice because people typically, the majority of the literature on this one is always a spacecraft crossing from one side of the X line to the other. This is because the reversal in the jet flows is a good way of finding such examples. In our case, this is a different story. Traveling practically normal to the CS, MMS encountered both the IDR and the EDR. The signatures of the IDR were breaking of the frozen condition in the presence of Hall, B, and E fields. And the EDR signatures included a strong out-of-plane current, positive energy transfer, and a temperature anisotropy, which disappeared at the field reversal. We derived some scale sizes, which are these here. We found the average dimensionless reconnection rate after taking care of at least of two sources of error rather carefully. Of course, as Kevin pointed out in his paper, there are other sources of error, but at least we took two of them, which we could do something about and did something about them. The observations and inferences are supported by Dpx simulations. Very good agreement in the reconnection rate. When we do simulation with observations, they suggest that the reconnection rate is in a steady state. And two, the 2D analysis is a reasonable representation of reality at the locale of MMS. Then we mentioned about the small asymmetries and their effects, and that the event was associated with the substorm onset, which began 7 minutes after the MMS observations. And that's it. Thank you very much for your attention.
Well, thank you, Charlie. You know, I was just clapping in the with the emojis. You know, it doesn't have quite the same impact that that clapping in person has, but I hope, you know, there's a lot of applause going off in the participants list. I love this. I love this talk. That's really nice.
Thank you.
Thorough analysis. So anyways, questions for Charlie? Yeah, Eberhard?
Charlie, this was a very nice talk. I really greatly enjoyed that, how in detail you got that out of this MMS data. And I have actually two questions. So it strikes me that the IDR is only slightly larger than the EDR.
Yes.
Yet the gyro radii, they are so much different. Say, how does that go together? Yeah. So is there a good reason that you can point to why that's the case?
Let me get the figure. Yes, the IDR, the width in that direction is about twice the EDR.
Yeah.
That's what I get. Now, let me see. But frankly, how to answer your concern, I
Well,
am
it's
not
not
sure I know how.
It's just a curiosity, since I thought, oh, normally I would have expected that to be much larger than the.
Yes, typically they show it something like 4 times as thick. Yeah.
Mhm.
And we have it only twice as thick. If you see here the with these twice and half as thick here, if you see the departure from guiding center motion, you see them very clearly, though.
Mhm.
I mean, you see, for instance, the electrons outside this area bounded by the green lines, the electrons, they follow the E cross B drift rather well. The blue trace, I'm saying, the blue trace. They only depart here. So yeah, well, yeah, that's it.
Yeah.
I think
Okay.
too, one of the other reasons that there's not such a huge, that may be why there's not such a huge difference in the sizes is MMS cut a little bit further downstream, like Charlie was showing. And so the sort of electron exhaust, electron parent sheet had opened up a little bit.
Oh, okay. Now that would make sense. So then, Charlie, I was curious. So in the simulations, you cited ion to electron mass ratio of about 100. So naturally, it's much larger. So it looks like that the simulations still represent pretty well what you see. Does that have to do with the fact that you are seeing the reconnection rate in a stationary, steady state, and if you have a different mass ratio, that might only impact any kind of temporal variations in that, or is there another reason that this?
Yeah, the reason which you posit could very well be the reason. Yes, it sounds good, because the reconnection rate is steady. The mass, the inferences from the simulations do not depend strongly on what mass ratio you take. Whereas if the reconnection rate is varying, strongly varying in time, then you are very susceptible to what mass ratio you actually choose.
Okay, okay. Well, thank you.
Very good point.
Great.
Thank you.
Who is next? I saw Eric's hand go up.
Yes, I was curious about the possible correlation with the twins ion heating event. And as you mentioned, Amy's method maps everything to the equatorial plane, which in this event is clearly not where the current sheet is located. So have there been any attempts done to do more sophisticated modeling with the of the tail that would be able to refine the location of the heating region?
I am not. I mean, there were some attempts apparently, but they were. It was found that the problem is not so easy, and as far as I know, they have not been continued.
Okay. Yeah. No, it's. Yeah. I'm sure it would be a difficult problem. Certainly, the first time you try it, it's difficult. It only becomes easy once you know the solution.
Yeah, right. Because here you have, of course, a model for a quiet magnetosphere, but now you have to have a model for a flapping magnetosphere, which is which is twisted and also reconnecting and all that. It might not be so simple.
Right, but maybe something like a TSO4, or if or if somebody's done a global MHD run of the simulation, use that field as your model.
That might be worth looking into. Thanks for the idea.
Tony.
I was actually just going to address that question that.
Sorry, Tony. I'm not sure if it's just me, but I can barely hear you right now.
I can't hear you either.
Well, let's just try this then. Any better? Apparently not.
Only very slightly.
Don't worry about me then.
You want to? I mean, I can still hear you. I think you can go ahead and ask.
No, I wasn't going to ask anything. I was going to help address the question. Amy's grad student told me, and I worked on that exact problem for about 6 months. And part of the issue is that a lot of that mapping is part of the fundamental processing of the twins data. And so it's a non-trivial issue to change that mapping. We were actually working on using various Tsiganenko models, but again, we had some issues with working it into the existing data processing from twins.
Yeah, and you mentioned the TSO4 too. I mean, that could capture the twisting, but there's no model, empirical or global MHD, that's really going to capture the flapping. As far as I know. Charlie, I had a question too. Can you remind me, did you have any thoughts on what might have caused the slight north-south current sheet asymmetry that you reported?
Which one do you mean? Oh, that you mean in the Hall fields?
I mean more in the density and temperature.
Oh, you mean the tail is usually doesn't have an asymmetry, and there is one here, right?
Yeah. Well, maybe it does. Maybe it is typical to have an asymmetry and nobody pays attention to it. Yeah.
Well, the asymmetry, well, you know, the asymmetry as asymmetries go. I mean, if you take the asymmetry at dayside magnetopause, you would be speaking here now in tens. Yeah, you would be speaking like the density on one side is this big, on the other side it's 10 times less or more or less. So here, when you look at this one, this asymmetry, if it were happening at the magnetopause people would say there is no asymmetry at all. So the asymmetry is very, very small. So the reason I drew attention to this one is to show how sensitive are the Hall fields to even a small asymmetry. So where this asymmetry came from, I do not know, but since it is so small, there's hardly, there's not something which one should worry about, I think.
Okay. Yeah, I wasn't sure if you thought it was related to the flapping somehow, or if it was just present, you know.
No, I didn't feel. I thought it was just present, basically. Yeah, to use your words. Not the flapping. No, I don't think it was related with the flapping.
Any other questions?
Can you hear me now at all?
About the same as before, but can still hear you.
It's clear.
Let's try this then, see if that helps any.
There it is, whatever you just did.
Cool.
Good.
Zoom was just being silly. No, we actually were trying to apply the Tsiganenko models to the twins, but again, because the mapping is done in the middle of the twins data processing, it wasn't something where we could just take an existing data product and reapply a different mapping to it. It's something that I think Tommy and Amy are still planning on working on, but as soon as we figured out that it was going to be a very significant time commitment to basically go through and rewrite all of the processing, it was abandoned in favor of easier results.
I think we can all relate to that.
Thank you, Tony.
Anyone else? Questions for Charlie? Well, if not, we are right at the top of the hour, so it's great talk with perfect timing.
Thank you.
So thanks again, Charlie.
Thank you.
Appreciate it. And yeah, we'll put the recording up online, though I guess everyone online has already seen it. So so thanks everybody. Thank you, Charlie.
Thank you.
Thank you. Bye. Great.
Bye-bye.